Thank you, Butcher. We are the Aerostar Delivery System team. My name is Adam Grassoff.
I'm Brenna Madison.
I'm Nathan Halstead.
And I'm Sam Wadula.
So our sponsor for our project this year is Aerostar. They are a company based out of Sioux Falls. They are the world leader in design, manufacturing, integration, and operations of the stratospheric balloon platforms. They have worked with companies such as NASA, Google, the US military, and many others to help them achieve their specific missions. So Aerostar is kind of split into two divisions. One side is radar, one side is stratospheric balloons. We're going to focus on the balloons because that is what our project will be integrated into. So they have the Thunderhead balloon and the Lightning balloon. The Thunderhead is just a lot bigger. The payload is a lot heavier, and it's made for longer duration flights, so like up to a couple months even, and that's the top balloon there. And then the Lightning is what we're going to be using at the end of our project. It is a lot smaller, based on a zero pressure balloon, which basically means as it goes up, it vents out air to prevent pressure from building up inside the balloon. The flights of a Lightning balloon are made to last for a couple days or a couple hours to a couple days. The payload is 25 pounds, so quite a bit smaller. And they can be hand launched from flexible locations. So in the future, we were hopefully going to test with some Lightning balloons. We can just launch from almost wherever we want.
So a little bit about our project. Our project is designed to drop a 25-pound payload from 75,000 feet, which is a standard height that Lightning balloons actually get up to when they're collecting data. So what are we trying to do? We're trying to make a guided payload that will land at a specific target location based off of where we want to put it. So that could be the middle of a field. That could just be somewhere that we know is a safe location and won't be like a lake. Because what they currently do is use wind data to kind of guess where their payload will land. So this will kind of help save them time and like energy to run around trying to track it. They'll know exactly where it'll land long term.
So our main goals and objectives, so kind of like what Nate said, we're detaching one of these Lightning FCUs, also known as a flight control unit, from a Lightning balloon and dropping it to a predetermined location. And this will all be done once it's given the coordinates. We won't have to touch a thing. It'll be totally autonomous. And the max distance it'll travel from the second it drops from the balloon to the second it lands is 10 miles. And then the location that it's going to land in has a radius of a quarter mile. And then one of the stretch goals that we had was to be able to integrate it into one of the bigger heads, one of the thunder heads, the bigger balloon.
So as Brenna mentioned earlier, we are doing this project for Aerostar, but we are fortunate to have a project similar to the one that we are doing called the NASA Floating Dragon Competition. And their project scope was essentially the same as Aerostar's, so it's a good baseline for us to start on. In the top left up there, that is Purdue University's design that they had, and they made a mini airplane that would rotate around their desired location where they wanted to land. The bottom right there is a parafoil made by South Dakota State University, and they made a design that would have 4 servo motors that would pull on the strings and guide it to where it needs to go. Then the bottom left there is a design by Princeton. They essentially made a guided missile that would rotate flaps at the top that would guide it to where it needs to go. Unfortunately, none of these really had extensive testing done, so there's almost no data on it. So we are essentially going to pick the South Dakota State University design because it is the easiest one to implement into the flight control module that Aerostar provided us. So we are going to go their route and pick it back off what they already have done.
So what are we doing for testing? In the top left, you can kind of see the testing drone apparatus with the carbon fiber tube running down the side. That was sponsored by Aerofly, which is helping us do these drone drop tests. Underneath, you can see some of our dropping apparatus that we've attached to the drone to actually make sure that we can collect data that we need, like acceleration and impact velocity for the actual unit. We want to make sure that we're not damaging anything on the Lightning frame itself. On the bottom right picture, you can see our actual release mechanism, which is a servo-controlled lever that'll help drop it when we specify. And in the bottom left, you can kind of see the parafoil itself guiding our control system and our electronic box, which is that orange box in the photo, safely to the ground.
So this is our wire diagram for our testing portion to get the data collection. It is made of three main components: the Arduino Uno, the MPU 6050 accelerometer, and a micro SD card reader. The MPU 6050 accelerometer would gather the acceleration in the X, Y, and Z planes, and the code that we created would calculate the velocity that we needed for data collection. And then the Arduino Uno will take that information and put it onto the SD card, micro SD card, and that is what we use to get our data and analyze it.
So here's a video of our test itself. Some things that we didn't account for was the force of the drone actually pushing down. So you can see the force of the drone actually pushed our paraglide out prematurely, and then we had a weight hanging down. We wanted it to hang versus actually strapping it to it because we only started with a 12-pound weight, and we wanted to be able to add weight after each and single test to actually get it up to that 25 pounds. And so it actually ended up causing some tangles with the paraglide lines and the weight. So when it actually drops, it'll drop not to the full potential. You'll see it actually start to spinning because the lines aren't able to be hold on the way they're supposed to. So here it drops, and you can see it start to spin and not do what it's actually supposed to. And so this kind of screws with our data just a little bit.
So what is our parafoil? It's called a modified Clark Y design, which is basically if you're going to cut it in half, that is the profile of what it looks like. That is just the airfoil design itself. That is not something we have control over. That is simply what it is. It's a 7-cell parafoil alternating between red and white. You can see each of those as it goes through. Each has 2 individual sections per cell with, for this calculation, or for later on, the calculation we used was 0.15 for a coefficient of drag, which is a good estimate between the 0.08 and the 0.2 that normal standard parafoils have. Our wing currently also has a 25 square foot area, which will help later in some of the other calculations that we did later. And that gives us about a 25-pound weight load, which is perfect for our design itself. We have an aspect ratio of 2.1 to 1, which means the long side is 2.1 times as long as the short side. And that leads to better stability and better handling, which are both key important things in our design, because we want to have good maneuverability to be able to steer where we want to go.
So because our parafoil got a little messed up, we wanted to do some theoretical calculations before actually looking at our experimental data. So the first one, which is covered by the zoom, is our average velocity. It ended up being 21.43 meters per second while falling. And then the next two are both drag forces in the y direction. So the first, or not drag forces, but forces in the y direction. The first one's gonna be your drag force. This is the force upwards that the parafoil is implementing on our apparatus, which is 104 newtons. And then the second one is the force downwards that gravity is implementing on the apparatus, which is about 114 newtons. And then we have a constant acceleration of 1.88 meters per second. And then as well as our final velocity being around 21 meters per second. Our force of impact, this isn't a true force of impact. This is a force that our apparatus feels while going down. The true force of impact, you need to do delta time or delta distance that it experiences on the impact. But since our weight was hanging at such a distance, this kind of messed with our results because it was over a longer distance and a longer time, so we didn't include it. And then the last two calculations would be our terminal velocity. These are just the fastest speeds that our actual apparatus could go. So seeing how we didn't get any results above the 24.34 meters per second showed our data was okay. And then actual experimental data, our experimental acceleration was 2.56 meters per second squared. This is just because our parafoil actually got messed up a little bit. So it will be going a little faster because less air is making its way into the parafoil. And then again, this is the force that the apparatus feels while falling. And then the percent error just shows that we did have some errors in our testing.
So going over some of the results, obviously the accelerometer gathered acceleration both the X, Y, and Z axis. But due to how it was orientated, our x-axis is actually the vertical. So that graph is the one we actually care about. You can see the 0 line across all 3, and the dotted vertical line is actually when we started testing. So those flat lines are when we had the drone on the ground getting ready to set up, and all the stuff before that flat line is when we are just simply getting everything in the box, attached, and all that. We wanted to just include it to just show that we were gathering data and wanted to include that. But the data we actually will care about is those big spikes after the flat line. That's when the drone was launching, hovering in the air, and actually getting ready to drop. And the last couple seconds, the last little bit of data is when we are actually dropping it. That's the force it's feeling as it's falling, or the acceleration as it's falling. And once the data stops, it actually got unplugged from the impact force of hitting the ground.
So from here on out, we plan on doing a couple more of tests from the drone. Pretty much the exact same thing that we previously did, just with some improvements. First being a more rigid design. That will also include better weight placement. So instead of having the weight dangling down, we're going to have it connected directly to our apparatus. So then there's less spinning as it falls, as well as the chute bag. We're gonna have that more rigidly placed so it doesn't kind of blow with the propellers of the drone. And then a smaller and tighter pull bag, so then the incident where the chute came out prematurely does not happen again. And then on top of that, we plan to bolt down our accelerometer and then make sure that it's orientated correctly, because usually the Z-axis is up and down, and in our case, we had an X, so we had to figure out what was wrong, and it was just that it was flipped.
So what's next for our project? This is the flight control module that Aerostar gave us. So our end goal is to eventually implement it into this CAD model over here. But before we do that, we do need to do a few more tests before we implement it. The first thing that we need to do is to continue to test without motors. In the video that you saw previously, it wasn't exactly how I planned it would go. So we want to keep doing tests on it, making sure that our chute bag works, the chute will deploy, and all that stuff. Then after that, we need to test with motors. So we want to make sure that the motors will pull on our parafoil and actually guide it where it needs to go before we implement it into the system. Once when all of our tests are done and we're ready to go, we will try to implement it into this. At the top there, where the open cavity is on the top, that's where Aerostar currently puts their parachute. So that is where we plan on putting our parafoil. And then on the left and right side on the top of the module, there are open cavities there. That's where we plan on putting our motors pending Aerostar's approval. And then also below all of this, inside of the flight module, there is a spot for a ballast bottle. And that will not be there when we are testing. So if we need extra room for electronics or extra room for a parafoil or anything like that, we have extra space to move down if need be.
So here's our Gantt chart, basically just a timeline of this semester and the future. Just to note, ours is going to look a little different than a lot of other groups because we are very test heavy this first semester, and then we're going to be design heavy next semester based on the results from our tests, whereas a lot of other groups are designing right now and testing their design next semester. So we recently completed the initial drone drop test, and then our next step is to do that again with the improvements. And then after that, we can get going on designing the motors and integrating it into the Lightning flight control unit.
So budget's obviously a very important part in any project. Ours looks a little bit different just because we have some supplies from the past NASA floating dragon competition. So some things we don't have to provide are like a paraglide, some servo motors to help control that, sensors like an accelerometer and GPS to actually position things and where we need to go. But we will need to still buy stuff like a battery, a Raspberry Pi, which is a microcontroller to help control how we are actually steering it, along with data collection, and a bunch of other miscellaneous things for testing like wires and 3D printing filament, as long as a testing budget. So when we do get to use a Lightning balloon, we have funds for helium and other miscellaneous costs that go along with that. So if we were to start this project from scratch, we've anticipated a budget of about $2,000. But since we already have some of the supplies, we're looking at closer to 1,000. Here are some of the references we used for coefficient of drag and just some of the photos that we used.
Now I'll open the floor to questions.
What altitude are you deploying the parafoil?
At the 75,000 feet, it'll deploy, which is kind of a concern because there's the atmosphere up there isn't as thick as it is down here. So one of our main concerns is actually the foil picking up the air when it's that high. So that's something that we have to work with Aerostar.
How long will it take to hit the ground from 75,000?
We have no clue. We asked Aerostar, like the floating dragon had a time limit, if I remember correctly, correct? But we asked Aerostar if they wanted a time limit, and they said the time doesn't really matter as long as it gets to the right spot and that it travels the distance that they need it to.
So if I remember correctly from your slides, the floating dragon had 4 control lines, and I think yours only has 2. What's the difference between how that's gonna be controlled?
Sure. So our parafoil is a little bit different than the one they used in the floating dragon competition. Ours has 2 steering lines, 2 brake lines at the back, so we'd actually have 2 fixed lines and 2 steering lines, whereas they had the option to control all 4.
You're looking straight on how much testing you can do,
No.
How high we can go?
how many times you
Well, the number of balloons they give us.
Yeah.
A lot. So.
How high were you able to get the drone compared to what you're gonna be doing? For your
So we were only allowed to take the drone to about 400 feet or so. So that is obviously drastically different. If we do scale tests with the lightning balloon, we'll be able to obviously take it much higher.
Will this be fully autonomous or will you control it?
It'll be done all
Mhm.
So.
So we want to just input where we want it dropped, and that'll be the only input that we give it. So once we hit release, it'll just go to that location.
Is there a max wind speed at all that I can handle?
Oh, not in our testing. We haven't found anything that would anticipate a higher wind speed being an issue.
How small is the area within which you have to land?
Half-mile diameter.
Okay.
What's the motivation? I mean, are we delivering packages to a private entity or something of this nature eventually? I mean, just kind of curious. Where it starts.
So it really will depend on Aerostar's customer. So they have payloads that are radios, communications, just general testing. It really is, it's different for everything. It's whoever buys the balloon from Aerostar. So yeah, basically it's whatever they wanted in the atmosphere or stratosphere. It does whatever it does in the stratosphere, and then what we do is just make sure that it lands safely, or that's our goal.
Kind of just makes it more efficient. They don't have to run out tracking wherever it fell based on what they think the wind did. It kind of just brings it right to them.
Think you'll be able to get it closer than the half-mile target?
Yeah, we kind of just we think it will be able to get closer. We kind of just gave ourselves that. They didn't give us a certain numbers for any of these. We kind of set them ourselves. They said, whatever you think you can do. So we think we'll probably be able to get a little closer, but we just gave ourselves that half mile.
I do know from experience that right now, whenever they have their estimate on where it lands, it's typically within a mile of where they guessed. So hopefully we can get it even closer than, because half a mile is still quite a ways from there. So hopefully we can get it even closer.
So your control system is gonna consist of pulling on these lines to control, so you have servo motors in there, I'm guessing. Pull.
Yeah, we don't exactly know how we're gonna design the controls yet, but yeah, we're gonna have some sort of way to pull the lines, and similar to if you ever go skydiving or something like that, you only have left, right when you are actually under a parachute. So it'll be act similar to that, just not hand.
Do you guys have any stretch goals that you don't know that you'll hit, but might want to?
Yeah, so our main stretch goal would be to be able to scale this to the Thunderhead balloons. And it doesn't scale the greatest because the motors, everything will need to scale, bigger parafoil, bigger motors. And then also Thunderheads have big long solar panels that come out of the side of them. So you'd have to learn how that affects the drag and how it affects how you'll turn your parafoil. So that's our main stretch goal, but we don't know if we'll hit that or not.
Any other questions?
All right, good job.